So, hello, my name is Veronika. As Liz said, I come here to you from Brno, Czech Republic, where I work for ThermoFisher Scientific as application specialist. And today, I would like to give you an introduction to the sample processing method for cryo-electron tomography, and then focus on cryo lift-out techniques. Okay. So let me start with a short overview of tomography workflow steps. When you want to do tomography, first thing which you do, you select your cells. Then you culture the cells. And after you have nicely prepared cells, you freeze them. Depending on your sample, you freeze them either with plunge freezing or high pressure freezing. If your cells are frozen, then they are loaded to cryo-FIB system, for example, our Aquilos 2 for lamella milling. In case your cells are fluorescently stained, you can do correlative light microscope targeting to ensure that your region of interest stays in your cell during lamella milling the whole process, at the beginning, during the milling, at the end. When you are finished with your lamellae, the sample is transferred to TEM, the tilt series is collected, tomograms are created, and then there's subsequent data analysis. First, I would like to focus on vitrification and the types of samples we can use. So based on your sample type, you can either do plunge freezing or HPF. If you have samples which are thinner, for example, proteins, viruses, bacteria, or cells, you can do plunge freezing. Basically, you grow your cells on the grid. After that, the cells are blotted, so there's only very thin layer of the cells left there. And then the grid with the cells is very fastly plunged into liquid ethane, and from there transferred to the liquid nitrogen. With high pressure freezing, we will have a really nice lecture on that later. So just very shortly, we have planchet, and into the planchet, we insert our sample. The planchet is then covered with another planchet and frozen. It's that simple. Here is the example how plunge frozen grid looks like. So this is the TN grid. Here we have it clipped in AutoGrid. This is the close-up of the cell. So all of these little blobs, those are the cells. And here we see the one cell from the milling angle. That's the angle from which we will mill the cell from the side. After our lamella is milled, it looks somehow like this, very thin lamella. And this is the view from electron beam, and this is the view from ion beam. In the comparison, this is how HPF sample looks like. So we have the rim of the planchet, and inside is the sample. This is the same. So this sample is HPF frozen yeast diluted in dextran. So after we prepared our sample, we transfer it to a cryo-FIB system. For me, I have been working for Aquilos 2. Let me introduce Aquilos. So it's a very versatile cryo-FIB system made for processing, manipulation, and imaging of cryo specimens. We have several applications you can use with this system. Let's have a look how it looks inside. So we have SEM column, then we have ion beam column. Aquilos is a gallium FIB. You can have easy lift cryo for the lift out. So you can load your HPF sample, pick up a piece of your sample, transfer it to another grid, and then go to TEM. I will be talking about this soon. You can have iFLM. If your cells are fluorescent, you can track your fluorescent signal all the way through the milling. For the coating, there is GIS and sputter coater. Here is the stage for the sample. The stage is cooled by gas nitrogen coming here from this dewar and from the outside. So basically the gas is cooled inside the dewar with liquid nitrogen, and then it comes to the stage and cools the stage. For loading the samples, there's loading station. And in there, we load the samples to the shuttle, this yellow little one. The shuttle is then transferred to transfer rod, which is pressurized, and the transfer rod goes to the load lock system, which there is little chamber, which is also pressurized. So that's how we ensure that samples stay vitreous. And the shuttle goes inside on the stage, and we can do our science. Here I have a video showing how ion beam milling is happening. So basically the ion beam mills, it mills away the vitreous cellular material. And at the end, we will end up with really thin lamella. And in TEM, it will be electron transparent, and then we can collect TIL series on it. Finish. Really good thing about Aquilos is that it has automation. I think everybody who ever tried manual lamella milling know how frustrating it is. And with Aquilos, we have big help with AutoTM software, which helps us to do the automated milling. There are a few user inputs which are necessary, but otherwise lots of steps are automated. Basically, user loads the sample, creates an overview of the sample, have a look how the sample looks like. Then you pick up your lamella site, the cells you would like to mill, and then AutoTM goes through preparation. In preparation, it finds the eucentric position where we see the same with electron beam and ion beam, and then it tilts to the milling angle from where we will mill our lamella. After that, it asks the user to select the lamella position. So if you have a cell and it's like your rounded cell, you can put the graphics where it will be your final lamella, and then AutoTM will do all the milling for you. So what I usually do, I set all of this before I leave work, and then overnight I let it mill, and then come in the morning and I have lots of lamellas prepared. The second application is cryo-slice and view. Just shortly about this, basically in auto-slice and view, you can also work with bulk samples, and you mill away slices with ion beam, and sequentially you image them with the electron beam, and then you will get this nice volume, as you can see on the video, which is then processed in Amira software. Then Aquilos also has integrated fluorescent microscope. As I said, it is great for tracking your fluorescent region of interest during the whole way of the milling. I will show you some examples of how I use it with the Liftoff. And finally, we come to the cryo Liftoff. So when you stand in front of Aquilos, the easy lift system for Liftoff is mounted right opposite of you here. On the inside, there's the rod, and at the end of the rod, we have the needle. And the needle is used for manipulating the sample. With Liftoff, you can work either with cells of grid and also with HPF samples. It's great for HPF samples because otherwise there's no way how to transfer the HPF sample to TEM. So basically, you have your HPF sample, your needle comes, you pick up tiny piece of your sample and transfer it to this other grid. We call it half-moon grid because it looks a bit like half-moon here. And it has these fingers. And at the edge of these fingers, we will attach our lamella. I will show you. Okay, so and now I would like to show you some results and manual how to do cryo Liftoff. First thing, we need to get our sample into Aquilos. For that, we have these new 35-degree shuttles, which come with slots for planchettes, both 3 millimeters and 6 millimeters. You can also load the sapphire discs if you have your sample frozen on that, both 3 millimeters and 6 millimeters. You can also have shuttle for 2 auto grids if you just don't want planchette, you just want the grids. You can also insert the Leica cartridge there, and it still supports the old shuttles, which were 45 degrees. So this is the close-up image of the shuttle for a 3 millimeter planchette. Here on the left spot, we load the planchette, and then it looks something like this. And here on the right spot, there goes the half-moon grid where we will be mounting our chunk lamella. So most of my images, which I will be showing you here, come from this Drosophila sample. It is a sample which was very kindly provided to me by Sven Klumpe from Max Planck Institute, and I'm very thankful to him for that. So this sample is frozen Drosophila eggs. These are the egg chambers, and inside them there are nuclei, and there's a GFP labeled nuclear pore protein, which was the target. This sample was HPF frozen and then trimmed in the cryo-ultramicrotome to reveal and just to get closer to the eggs. After you load your HPF sample, sometimes it's contaminated from the freezing process. You know, like when you separate those both planches, there will be sometimes lots of ice. Unfortunately, with HPF samples, it's really easy to get rid of this ice. If we compare it to cells on grids, there, when you have ice contamination, you can't do much about it, but here you can. So it's really easy. We call it shooting away the ice. So basically, with the ion beam, we just zoom in and zoom out, and the ice just poofs away, and it's gone. So this is before, and this is after I cleaned the area. It can take long. Like if you would like to clean the whole grid, you can prepare a whole afternoon for it. So usually I just select one area which I like and clean the area and just ignore the rest. The second important thing is to do the coating. The HPF samples, they charge a lot. You can see here the lines from the charging. Also here on this image, the ice is very bright, it's charging. So after you coat it with spatter coater and GIS, the charging disappears and you can work much better with your sample. Like you start to see your features, and here you even have an idea like where your sample might be. Since not of all the samples look like this, as I showed you on the first images, sometimes all you see is just gray, and you don't know where to mill, and it's I think 2.5 millimeters of gray, so that's lots of gray. So you need to know where your sample is. For that, we have iFLM, and it's very useful, especially for this use case. So here are some examples. So these are the Drosophila eggs I was talking to you about. With iFLM, I scanned a whole planchet, whole area of the sample, and found this one egg chamber with lots of nuclei. So I liked it, and I decided to use it. After zooming in, I selected this area for my lamella. Like here, I want to mill somewhere around. So this image comes from the MAPS software. It's software we use for taking overview images and for the correlations. So in MAPS, we do the correlation and we find out where our area of interest is. But then we have to mill. So we have to go to ion beam and find something which will help us to navigate. For that, there are several options. The easiest one is just use some ice particle. For example, here, I use this ice here, which is also visible here. If you don't have any ice particles or you just can't find which one is the right one, you can just mill some fiducial there. So what I usually do, I just mill the X mark somewhere near where I think my region of interest is. It is important to have the fiducial like close to your region of interest, because if it's further, and then you do these measurements, I will show you in a minute, you might not get the right spot. So get your fiducial closer to your sample, but just be careful to do not put it in the sample, because it happens also to me that I just milled the fiducial, then went to iFLM, checked the fluorescence, and fiducial was right in the middle of my region of interest. So just be careful. Then in MAPS, I do the measurements. So I find the fiducial and just figure out like where my region of interest is from my fiducial. Then I go to ion beam and do basically exactly the same. Find the fiducial, apply the measurements, and then place the patterns. So these patterns here, they are for the trenches. We have top trench and bottom trench. If you want, you can also do this side range, which I personally really like because it allows me more motion with my needle. I don't have to be scared that I will just crash the needle to the sample, but it's not necessary. You can have only the top and bottom trench. So you apply the measurements, which the same as you did in the maps. And then you figure out like, okay, so my region of interest should be somewhere here where my pointer is. And then you place the patterns above and under, and you can also do the side range. With the side range, the only thing you have to make sure is to make it on the good side. So if you make it on the right or left, it doesn't matter. It just has to be the side from where your needle comes in, because otherwise it won't work and you won't be able to connect the sample. So before milling the trenches, just insert the needle and check if it's coming from right or from left, and then put your side trench there. So this is how it looks then this is how it looks from the ion beam view. So these are the trenches, and this is the chunk which will be lifting up, and it will be our future lamella. Then, so this is the view from the top. Then we tilt it, so we see the chunk from the side. And since HPF sample, and it's very, very thick, we have to somehow disconnect our chunk from the rest of the sample. And for that, we use these undercuts. And basically, we mill away the material, which is not visible anymore in these patterns. And only thing which holds our sample, our chunk, is now this part. Just be careful to do not make this part too thin, because sometimes it might happen, especially if your chunk is too long, that it starts bending and you will get some cracks. So it's always good to, like here, this is the GIS, the white part, and then leave some space under the GIS, because if you would leave only the GIS, it might crack, so leave some cell there also. Here is the example of how I milled several trenches. So here I selected several regions of interest, and this is how I milled the trenches. Since the lift out takes longer than normal manual milling, and it takes so much effort from you, you just want it to be right. So it's good to prepare several sides and then lift them up one by another. It's much better than doing it just first one lift up, second one lift up. The timing will be shorter, and you will also have better feeling that you have done so much. Here is an example. Like I wanted this part to be in my chunk. So this is the chunk. And then I went to iFLM to see if I caught the right spot. So if in my chunk I have the spot I wanted. So it's not very well visible, but basically here is the trench, and here is the trench, and this is the area, and it's exactly the same area as here. So I was very happy that I got it. Now let's pause for a minute from lift out, and let's talk about attachment method. So this is how you will prepare your sample. You mill the trenches, and then you do the undercuts, and your sample is ready. But now you have to think about how you want to attach the sample to the needle. So there are several options. First, which is I think the most widely used, is just to use GIS. The second is to do redeposition from the needle. And the third is attachment with a copper chunk. I will go through all of these. So the attachment with the GIS, I would say it's the easiest. So if you just start with lift out, just do this. Basically, what do? You mill the trenches. You can see them milled here, and you insert your lift out needle. After the needle is inserted, you also insert your GIS needle. After that, you touch your sample with the lift out needle. This is important because if you would touch your sample and then insert the GIS needle, it might cause some shaking, and then the needle may somehow destroy your sample. Well, and then only thing you do, you just open the valve for GIS and let it flow. And you can see it grow. It's actually kind of funny. And after a while, your needle will become like fluffy, like fluffier than it was. You can see the difference between here. This is like before, and this is the after. Like it's fatter now. So this is the ion beam view, and this is electron beam view. And this is the example of where I accidentally put too much GIS there. You can see the whole sample is very fluffy now, but it worked. The only thing was that then I have to mill away all this GIS, and it took a long time, but it worked. So even if you accidentally put too much, then it's okay. One thing with GIS is that this method is a bit messy. That means you have to code your samples before milling. So you already have one layer of GIS there. Then you add another layer during the attachment. So there's 2 layers of GIS. Sometimes it can happen that the GIS will fill if your trenches aren't wide enough or big enough. The GIS can fill the trenches, and then when you try to lift up your chunk, it just doesn't want to go. So then you have to just unattach the needle, mill everything away, and then try it again, apply another layer of GIS, and so you end up putting more and more and more GIS until your sample is completely covered with GIS. So this method, you can use it, I don't know, maybe twice at one sample. So you can't use the sample anymore after, because there's so many GIS that if you created your lamella, so your lamella would be like this much GIS and then only a tiny bit of your cell. Okay, so that's the disadvantage of this method. Then there's another method where you can work with redeposition. What does it mean? So you take your needle and you come to your sample. Then you place a pattern here on the needle and mill to the needle. And as milling is going, the material gets redeposited, like spattered from the needle to your sample, and it sticks the needle to the sample. And you only need to place like 2 or 3 patterns here, and it should stick together. Then you will be able to see little holes in the needle, and also some like little indentations which are coming from the sample. So you know the material definitely is there, the material which is sticking them together. Then what you do, you just cut away this and also this, and just lift it up. So that's the redeposition from the needle. For me, this sometimes doesn't work. But for some of my colleagues, they work with it regularly, and it's okay. So it really depends on your preferences. And now I will show you my favorite method, which is the third one, and it's the attachment with the copper. So we use it almost similarly as before. We use the redeposition to just stick things together, but instead of redeposition from the needle, we use this copper chunk. So how it works? Where do we get the copper? We use the half-moon grid. So the half-moon grid is from the copper, and here on this area, we will attach the lamella. And for the chunk, for our lift out, we will just use some of this. So we do exactly the same as we would do from our sample. So we place the patterns, which will create these trenches. Then we will make it little smaller. So you cut away here, and you cut away part of here. So at the end, the sample is still attached like down, and also here on this side. Now we tilt it, so we are looking like not from the top, but from the side, and do the undercuts, exactly the same as we did on the sample. So right now we cut it from the bottom, and it's just now holding here on this part. It's very important that these undercuts are properly milled through, like you don't see any leftover material there, because it often happens that, especially like somewhere in this area, it gets stuck. So then you come with your lift out needle. So for this, I would use like new needle, or if you don't have new needle, no problem. You just have to make the needle, like the tip of the needle flat. So you just place the pattern there and make it flat. And you also place the pattern on the copper here to also create the flat surface. After that, you do the same as we did before. So you place the patterns, and right now the redeposition is from the copper to the needle. So the needle is tungsten, and the copper is much like softer and nicer to work with, and the material is more stickier. So it's better. The redeposition is very easy. As I said with the before, the tungsten redeposition, sometimes for me it doesn't work, but this one, it works every time. It's very easy. So you place the pattern and you mill away pieces of copper, and the material is spattered to the needle, and it will like stick the needle together. After that, you just mill away this piece, which is holding it together, and lift it up, and then lift it up a bit more. So you end up with the needle and this little piece of copper you have there. So I'm usually using like this size of the coppers, but you could experiment, make it bigger, make it smaller if you want to use it just for one time. If you make it bigger, you can reuse it several times. So that's an advantage. So let's continue with the lift out. We have our sample prepared, and we have our copper attached to the needle. So I have lots of examples of this method, so I will continue with this method. So you come to the sample and touch it. When the needle with the copper touches your chunk, it will like move very tiny bit. So then you know it's there. Just don't be scared. It's okay to move it tiny bit, like not too much, but only so just it little, so it jumps a little. And then you know, and sometimes when it touches, you will see the charge, like the whole image, which will for a moment be like whiter. It's not that much with the copper piece, but when you touch it with the needle, then it works really nice. Like you see the like contrast brightness goes whiter. Okay, and then you place the patterns and you place them on the on the copper. So you want the material from the copper to stick to your chunk. After that, it looks something like this. And then you just cut away this holding piece. You can see we are basically doing the same thing over and over, just with different things. And this is how it looks when it's unattached. So it should hold. It should hold on the needle through the copper. And sometimes it's really funny, like after you lift up the needle, you can see like how this tiny thing can hold such a huge lamella, but it's no problem. It just holds there. Sometimes it even happens that when you don't place the patterns correctly or something goes wrong, sometimes it just holds the lamella simply on electrostatic. Yeah, so the tiny piece holds the lamella very nicely. You can see I have these chunks with different sizes. So the size depends on your sample. So when you use the iFLM, you can see like how deep is your region of interest. Based on that, you have to create your trenches. So if your region of interest is somewhere like here under the surface, your trenches don't have to be that big. But if it's much lower, like in depth, then you have to create like really big trenches. I would say like at least 30 microns in Y direction, because then when you tilt when you tilt the sample and do the undercut, you want them to be as low as possible, and you will be able to see that only with these big trenches. So if you have your regional interest very deep, you do the big trenches. Okay, so the next step. So right now we successfully taken the sample from our planchette and we have it up in the air. And now we go to the second grid, to the half moon grid, and we will attach it there. So here is the half moon grid, it's clipped in the outer grid, and here are the fingers, and we will attach it here at the top. Yeah, sometimes you can even, like especially if your lamella is very long, you can cut away like piece of like the front piece of the copper finger to make it straight, so your lamella nicely touches it. You can also cut away like piece of the lamella to make them fit together nicely. So then you go closer to your finger and you touch it. This might seem very scary for people who especially do it for the first time, but after you do it several times, it becomes the best part of the lift out, and it's kind of fun. So you want to touch it, so tiny piece of your lamella is sticking up, and the rest of it is just like from the side. Then this is electron beam view, so we see it like from the side, and this is ion beam view, and we see it more from the top. So here we again place these patterns, which I am using over and over and over. We place the patterns and do the redeposition again. So we mill away a piece of copper and it sticks to the lamella and it holds there. And sometimes you can do just a few patterns. For me, I like to do lots of patterns because I feel safer. Like the more, the better. Some of my colleagues are making fun of me, but I think it's nice to have them more. And so you want to know if it's right. So when it's right, it looks something like here. So you see these little triangles, which are sticking from the lamella to like this one. This is the first one, it's the best one. You see these little triangles of material, which are sticking out of the lamella towards the copper. And that means it holds there, it's nice, it's good. You can continue. In case you don't see them, or you are not able to do this, what you can do, you can just insert the GIS needle and flow GIS needle there just to get it sticking there. I wouldn't recommend that much because it will get the GIS on the whole chunk, and then you will have to mill it away and it will be pain. It will give you like another hour of work. But if you are just not sure or you just can't do the connection, just put GIS there. Yeah, and then the last step of this is that you mill away this piece of copper which is touching. So you can see there's still a lot of that left, and you can use this for 2 or 3 another more lift outs. And then you just retract the needle, it will go away, and you have your chunk nicely attached to the finger. Now to the milling. So what we do, we had our chunk attached and we saw it from the front. So right now we have to tilt. So we see from this side. Basically, we see the front of the lamella now. No, this was the top, this is front. So you tilt and you mill. And this milling is basically the same as you would do some standard milling of the cells. Basically, just tilt to the milling angle and place the patterns there like this. You mill away this material, then you lower your current, you move the patterns closer, lower your current again, move the patterns closer, and you will end up with a really thin lamella. Here are some examples. So this is a lamella, which is or chunk lamella, which is attached to the finger. I want to see if I still have the fluorescence signal inside and how it looks like from this angle. So I went to iFLM and collected fluorescence. This image is fluorescence and reflection at the same time. And here is the fluorescent signal correlated to the SEM image. Then I milled lamella to around 700 nanometers. This is view from the ion beam, like we see the lamella from here. And the second image from SEM, we see it from here. And again, I collected the iFLM and checked. So during the milling, I always tried to every several patterns away, I tried to go to iFLM and check if I still have my region of interest in the lamella. So I collected the stack and then I went through the stack and saw if I saw that my region of interest is more on the top of the stack, then I milled more from the bottom of the lamella. So if I saw that it's in the middle, it was okay. You just milled the same from the top and the bottom. But if you saw that it's not in the middle, it's more down or up, you just milled the area where it wasn't. And that seems to work pretty well for me. So this is lamella fins to 400 nanometers. Again, I checked. You can see that the fluorescence signal is getting weaker, but it's still there. And this is the final lamella around 200 nanometers. Okay, so this is the whole lift out process. If you will have any other questions, just let me know and we can talk about later. I have some videos I can show you. If you need some tips, tricks, we can talk. I have just a couple of few last slides. So let's talk about the challenges. Of course, a lot of things can go wrong. For example, your surface of the cell, your GIS layer might not be that nice. It might happen that you have some contamination, which is like inside the GIS, or during the milling, the GIS might get cracked or just peel away. And then if it's okay to lift this lamella up, but if you lift it up and attach it, then you have to mill it. And during the milling, all of these irregularities, they can cause curtains, they can cause breakage in your lamella, and you don't want that. So actually this one has really easy solution. So after your lamella is attached, you just mill away the top layer of the GIS, you insert the GIS needle, and you insert new GIS layer. The bad thing is that the GIS will not get only here, but it will also get here and here and here and here, and then you have to mill a lot again, but it's doable. The second thing is that your chunk might not be that pretty as you thought. Like here, this one during the lift out, it looks pretty nice, but after I attached it, I saw that the front is horrible. Also, here was the huge hole, and there were some holes here. So even if I would mill through the lamella, I would just have lamella with holes. So if you have something like this, I would just leave it and do another one. Another example is when your lamella, when your chunk will fall. So this happens when your attachments to the needle and to the copper is not strong enough. And when you try to lift it up, it will just fall. So for this, I would just make sure that you can see these indentations, like the triangle ones on the sample. And then when you see the triangles, that's good. If you don't see them, you can apply the patterns one more time, for example, that helps. Especially new people who are trying this and are scared of this. So what can happen is that you will crash. You will crash your needle with your chunk attached to the finger. So instead, or it should be like straight, this straight. But in this case, it got bended, and now you won't be able to attach them. If you are very, very patient, you can try to play a lot with the needle, move the needle, try to touch the finger. For example, if it's like this, you can make it straight and so on, but it takes lots of patience. And so if you have a very special sample, I would try, otherwise just start again. And the last thing is lamella bending. So when you mill and you are getting closer to your final lamella, it often starts to bend. And you can see here, we have the front, and here is the back. So the front part of the lamella is lower. And now you can't mill that much, so your lamella will end up very thick. And then there's the ice contamination. So my advice is, after you finish your final lamella with lift out, you always go straight to TEM. Because if you store your lamella, it will get so much ice you won't even see the lamella. You can see here I did some experiments. This is not the final lamella, it's just the chunk attached. So I attached it and stored it, and then had a look and then stored it again. And you can see how the ice grew there. So if you have just the chunk, like very thick lamella, you can store it, it's no problem, because then you will be able to mill the ice away. But if you have your final lamella, just go straight to TEM and just be super, super careful. Like take face mask, take face shield, do not breathe, warm everything, really, do not breathe or try not to breathe. Warm everything, warm your tools, warm your loading station, take a fresh nitrogen, not too fresh because you need to wait like 5 minutes until all the nitrogen, all the ice particles gets like settled down at the end of the viewer, but don't wait too long. Like I would do sometimes between 5 and 15 minutes after the loading. Just you have to be so careful and just don't breathe. And just hope that you won't get any contamination. You can see this one is amazing. So this is the lamella, the small one. Okay, and here I have just some example of the lift out we did on from the grid sample. You can see you can also attach your lamella here on the side. It gives you a bit complication because then you have to figure out like how to orient it in TEM so I can get some tilt series, but it's possible. But for me, I like it more here. It's easier for me. It's easier for TM guys to just work with it. And here's another example of the lift out from the grid. So you can see it's also possible from the grids. It's actually much easier from the grid. So if you want to start with lift out, I would start with this, just train on this, and then you can move to HPF, and it will be much easier. And here is some literature in case you are interested and want to read something about the lift out. Here are all the sources. And with that, I will finish my presentation. If you have any questions, just ask.
Already one more question. Hi, great talk. Thank you. I was wondering if the copper is generally better for the tungsten than for the lift out. Is it possible to produce a copper coated needle as opposed to needing
Yes,
to
there are some actually. I think they use them in either material science or semi. So it's possible. Yeah.
Oh, cool. Thank you.
I think in one of your examples, a cryomicrotome was used before going to the Aquilos. Could you describe like in what cases you would need to do that?
Yeah. So sometimes it happens that your sample gets like at the bottom of your HPF planchet. Like for example, with this X, what I think they just observed that after, if they don't cut it with microtome, they are not able to get to the sample. So that's why they just cut away the top. So it's easier to get to the sample. So you don't have to do very, very long lamella, because if you don't cut it, your lamella would have to be huge. So you have some of your region of interest there, and you don't want it. So it's better to cut it. I think it might be useful for lots of samples. Because not only you will cut it, you will get a really nice straight surface. So you don't have to deal with all the indentations and irregularities of the surface. And also you will get your region of interest really close to your surface, because when you mill the lamella, like the front is nice and thin, but the longer you have it, like the end not that thin. So it's the best if your region of interest is like at the, like here's the front, like somewhere here. So the cutting might really help.
Yesterday we mentioned that could look at biofilms. Would you expect to have to use the lift out method to be able to look at biofilms because of their thickness of bacterial cells?
Probably. I think maybe, Liz, do you have any experience with biofilm here? Yeah, I think it should work also like on normal grid. One more time, I couldn't hear you.
From online, how would you know the depth onto which you should mill the cells during FIB-milling with the help of CLEM?
Yeah, without the phlegm, you wouldn't. But with the phlegm, it's really easy because what I usually do, I just find the surface in reflection, and then since you know your slice distance, you know like how deep is your sample like from the surface. But without, you would just have to trust and hope. Or you could do, you could also do just some really fast cross sections and see. So the cross section will open your sample in one, and you will be able to see it like from this side, like this is the top of your sample, and you will be able to see this side. And if you don't see there anything, then it means your ROI is really, really deep.
I think we can probably do at least one more. There was a question about the slice and view, and the person online was interested in knowing which instrument was that from.
So this was from Aquilos. I would say our best tool for auto slice and view is definitely Hydra, but you can also do auto slice and view on Aquilos. It's no problem. The software is there, and if you just have some HPF samples or any other samples, you can do it.
I think we'll pause there unless there's any other questions in the room. So let's thank Veronika again for a really fantastic talk.